So today's topic is topological sort. Topological sort, right? So what is it? Is it basically a linear ordering of vertices in the directed acyclic graph, DAG, right? So such that for every directed edge u and v, for u and v, vertex u should come before v, right? So let's say we are having this edge, right? U is connected to v, right? This is the edge. Then we need to sort this in such a way that u should come first before v, right? So, and it is only applicable for the directed acyclic graph. What is directed acyclic graph? Basically it should be directed, right? So direction should be there. Let's say a to b, right? It should be directed. It should not be undirected, right? This is not valid. Okay, it should be directed acyclic. Cycle should not be there. Okay, let's say here we are having this c node also, b, then again c to a. So this is not in the case, right? Cycle should not be there. So a should not be reach again, right? If we start from the a, it will go to b, it will go to c, again it is coming to b. So this is a cycle. It should not be a cycle. So this is the valid DAG, right? So this is the DAG. Now this is only applicable on the DAG. What else? Let's say we need to find the topological sort output for this graph, right? The simple idea is u should come before v, right? So let's say we have started from 5 came, then we will go to 2, then 2, right? Then 3, then 3, then 1, then 1, then what? Then again this will go to 0, okay, 0, but 4 should come before 0. So it should be 4, then 0, right? This is one of the valid topo sort output for this. One of the valid. It can be other also, right? So if you see this 5 is coming before 0. Yes, it's coming before 0. Is it coming before this 2? Yes, right? Is it coming before this 3? Yes, it's coming before this 3. Same with 1, right? And but this is one of the case, right? 4 should come before 1. So 4 should come before 1, right? So this is the valid output. Got it? What is the logic behind this sort? For any edge u to v, u should come before v, right? So if you see any two nodes, let's say 5 and 1, 5 is coming before 1, right? So we can say this is valid, right? Now how can we do this? How can we get this output? We can do topological sort using DFS also, DFS using BFS also, right? DFS is what? Recursion, right? Recursion, we will go in the depth, and this is basically queue. We will go level by level, right? So let's first check the DFS approach. Okay, so here's the approach. There are two approaches. One is DFS, one is BFS. Okay, and for the DFS, what we will do? Okay, before this, where this topological sort is used in task scheduling, right? Course prerequisite. This is the important question on Leetcode. Okay, this is asked in Google and Amazon. After that, compilation order, like which item should be compiled before, right? Earlier. So these are some use cases. Let's move to the DFS. Okay, what is the key idea? Perform DFS on returning from the DFS call, push the node to the stack. Okay, we will be using stack in this topological sort. Okay, how? Now how? Let's check out the example. Okay, we are having this example, right? Now we will be using stack. stack will be there. Okay, and one more thing, visited array should be there, so that we will not traverse the element again. Okay, if it's already done, then we can say we are not proceeding with this array or this node. So 0, 1, 2, 3, 4 and 5, right? This is the visited array. Okay, we will start with 5. DFS start with 5. Okay, 5 we will put 1. Okay, then what else, what we will do in the DFS function, it will check for its, in the DFS function what we will check, adjacent neighbors. Okay, neighbors. Okay, it will check for all the neighbors. It's 0 and 2, correct? So we will push 0. First we will check if neighbor is not visited, right? If this is not visited, then we will do what? We will call the DFS for this neighbor. Okay, we will call the DFS for this neighbor, and this will repeat for all the neighbors. Let's say we started with 0. We started with 0, correct? 0. It will call the DFS 0. After that, is there any other neighbor for 0? No, it's not, right? Because this is a directed graph, correct? So there is no out edge, right? So we can say it's completed. It will come back, right? So 0 DFS call for 0 is completed now. After checking the neighbors, it's not there. We will push this 0 into the stack. Okay, stack dot push this node. Okay, node. Basically we call the DFS for the node, correct? So 0 is there in the stack, right? After that, it will come back. It will come back to the 5 and check for the second neighbor for 2. Right, again it will call for DFS2, right? From DFS2 we will call DFS3 because this is the neighbor, right? DFS3, and from that we will call what? DFS1. At this point there is no other neighbors, right? So we will push in the stack, pushed in the stack for 3, right? This is done. It will go back to 3. Push in the stack, 3 is done. 2, it's done. Push in the stack, right? So this part is completed. Okay, for this node is completed, this node is completed, this is completed, this is completed. Now 4 is remaining, right? So we will check for the 4, DFS for the 4. Okay, now it will check for the neighbors, but they both are already visited, right? So okay, before this 4 we will also push 5 because 5 is completed. So now 4 neighbor are not there, so we can simply push into the stack 4. Great. So now we got this stack, right? Let's pop out the element from this. 4, 5, 2, 3, 1, 0. Now I can say this is the output and this is the output of our topo sort. Is it in the order? Let's check. 4 should come before 0 and 1. It's coming before 1 and 0. It's correct. 5 should come before 0, 2, 3, 1. 5 is coming before all the elements. Correct. 3 should come before 1. 3 is coming before 1. Right. 2 should come before 3 and 1. It's coming before. So this is the valid topological sort output. Clear? We are just popping out the element from the stack and we got the output. It's the simple DFS approach. Understood, everyone? Basically what we are doing, we are starting from the element and we are going in the depth of its child, right? This is the last element, so we will push this because this is the smallest element. We can say this should come at the last because there is a dependency of 3, right? 1 and 3. So we will push this one because there is nothing after this. So pushed 1, after that we will push 3. Okay, 3 should come before 1. So like this. Shall we code it now? So let's code it. Okay, so here we will be having the adjacency list. Okay, and the, let's say in this topo sort function we will be having the number of vertices, the number of nodes, and the adjacency list. Okay, of type integer, correct? adj. What else? What we need to do now? See, first we need to make a boolean array, right? Boolean visited array, visited equal to new boolean of size v, correct? Then we will be using stack, right, of type integer, st equal to new stack, correct? After that we will start the DFS for all of the elements, right? For I equal to 0, I less than v, and I plus plus, we will check. If this is not visited, we will call the DFS. F visited of what? I, then we will say DFS, and in the DFS we will be passing this I, the current node, and the visited array, and the adjacency list, and the stack, correct? Okay, so let's write the DFS function. DFS, and that first node is there, then what? Visited of type boolean, visited, then what? The adjacency list, that is this one, and the stack. Okay, so stack of type integer, st, right? Now what we need to do in the DFS? We will first make this node visited, right? So visited of node is true now. Now we will call the for loop for checking the neighbors, right? So int neighbor on adj.get what? Node, right? From the adjacency list we will get the neighbors, right? We will check then if this is not visited of neighbor. If it's not visited, then we will call the DFS for this node visited adj stack, right? So after completing the call, after checking if there are no neighbors, then we will push the element in the stack. Dot push what? Node, correct? So this is the simple approach, and let's say after getting the stack, we will print the output for int I equal to 0, I less than v, and I plus, or let's use the while loop, while stack is not empty. Stack is not empty. What we will do? System dot out dot print. What we need to print now here? This stack dot pop, right? The element at the top each time, right? And what else in this? Now we need to make the adjacency list. This part is clear, right? The topological sort, the code, what we are doing. Basically we are checking for each and every element. If this is not visited, then we will call the DFS. Let's say we were having this graph, right? We started with the 5, correct? So in the DFS it will cover, in the DFS call basically it will cover this 2, this 3, this 1 and this 0, right? Because these are connected, but from the 5 we can't reach 4, so 4 will remain, correct? So we are using this for loop. So in the for loop it will check all other nodes, they are visited, it will go to 4, then again it will call this DFS function, correct? And in this DFS call, what is happening? We are basically making it visited the node. After that we are checking the neighbors. When the node has no neighbors, then we will push the node in the stack. Got it? Okay. And for this main function, let's make the adjacency list now. So let's say we are having the size v equal to 6 nodes from 0 to 5, right? Then list of integer adj equal to new array list, right? Then what else? We will start from we will basically put the initialize the array list for each of the inner list, right? I equal to 0, I less than v, I plus plus. So adj dot add new array list, correct? It will basically initialize the array list for every list inside the list, correct? After that, let's make the edges. Let's add the edges. Adj, first one was from 5 to 2, adj dot get 5 dot add 0, not 0, 0 is also there. Then 2, then from 2 to 3, 3 to 1, what else? 4 to 0 and 4 to 1, 4 to 1, right? And after that we will call this topo sort with the value v and what else? adj. Let's run this. Okay, we need to call for neighbor. Okay, we got the output. What is the time and space complexity here in terms of v and e? See, basically the time complexity will be o v plus e. How? Because we are checking each and every node, right? We are checking each and every node and we are checking each and every edge also. So it will be o v plus e. V is the nodes, e is the edges. Edges is basically the neighbors, right? And space is also o v plus e, because we are having the adjacency list, right? And here we are taking the space v, and again stack will take the O of h. H will be the depth, the maximum depth. So overall it will be O v plus e if we are using the adjacency list. If adjacency list is given to you, then it will be O of v only. Okay, so let's see this BFS approach now. Okay, so basically this is also called Kahn's algorithm. Okay, And what is the key idea? Now here one term is there, in degree. What is in degree? Before proceeding to this, what is in degree? The number of incoming edges. Number of incoming edges, right? Let's say for this 0, what is the in degree? It's 2. From 5, 1 is coming. From 4, it's coming, right? So total 2. For 2, it's 1. For 3, it's 1. For 1, it's 2. For 0, for 4, it's 0. For 5, it's 0. Correct? Understood? What is in degree? Number of incoming edges. Basically, what we can say? Let's say we are having this 5 and 0. Let's check U and V. In the previous question, what is the topological sort? It says U should come before V, right? Correct. And what is in degree? It is the number of incoming edges, right? So for 0, 1 from 5 is coming, from 4 is coming, right? So we can say 5 should come before 0, right? Before 0. Same with 4, right? 4 should come before 0. And in degree of this is 2, right? So we can say there are 2 nodes that should come before 0, that is 5 and 4, right? So with the in degree, we can know like what is the number of nodes that should come before that current node. Correct? We can say this is the definition of in degree, right? What is the number of nodes that should come before that current node, right? Now when in degree is 0, what we can say? We can say there is no dependency, right? There is no dependency. We can add this. We can add this in our array, right? There is no other nodes that should come before this particular node. Understood? Okay. So we are having 4 and 5. These are the nodes with in degree 0, right? We can say there is no dependency. We can add this in our array, right? So we can add this in our array, right? Let's say 4 and 5. Okay, correct. This is the order. In the result, if you see, where is the result? This is the result, right? 4 and 5 are coming first. So that means if the in degree is 0, we can add this in our result, and then we will proceed the neighbors of these 2 nodes. Again we will do what? Let's say we have pushed this in the result. We will check for the neighbors. Okay, so let's see here. Push all the nodes with in degree equal to 0. We have pushed 5 and 4 in the queue, right? After that, while queue not empty, pop the node. We will pop. Let's say this is the queue. We added 4. Let's say 5 first. 5 and 4. Okay, we added this. Now we will pop the node. We will pop this out. And add in the result. 5 added, right? After that, added the result. Now for each neighbor, reduce its in degree by 1. This is important thing. Okay, now what else? What are the neighbors of 5? It's 2 and 0. Okay, now we will proceed these neighbors. Okay, as we are doing in the BFS part, right? We are checking the neighbors and we are adding them in the queue. But before adding them in the queue, we will reduce their in degree. In degree of 2 will be minus minus. Why? Because see, what is the node coming to this? It's 5, right? 5 was the dependency. We already added this in the result. That means this is already done. This part is already done. We will reduce it. So from 1 it will come to 0. Right? Understood? So this is one of the step while checking for the neighbors. After that, this is basically for the neighbors. Okay. The second step will be push into queue. Okay. And repeat the same things with all the neighbors. Great. It's clear, right? This was a simple step. First let's write the steps here. Let's say first count the in degrees for all. Second step was push all nodes with in degree equal to 0 in queue, right? Then start traversing the queue. Start traversing queue, that is while loop, while queue is not empty, right? After that, what we will do? Pop the element. Push in the result. Check for neighbors and reduce their in degree by 1. Degree minus, correct? After that, push into the queue, and that's it. This will go on, right? Again it will go to this thing, the pop the element, again check for neighbors, reduce the in degree, push into the queue, correct? So if you talk about this particular example, how we will proceed, let's check it. So we are having this result and we are having the queue also. So first we will push what? We will start with 5 and 4. For 5, neighbors are 2. Let's write the in degree. It's 1, it's 2, it's 2, right? So 1 and 0, right? So we will pop this out. We will add in the result. We will check for the neighbors. Reduce the in degree at 0 now. Reduce the in degree for this one, right? 1. Now we need to push the element with the in degree of 0, right? We need to push the element with the in degree of 0, that is 2, right? So we will add 2. After that, we will pop the element. Which one? 4 is there, and again check the neighbors 0 and 1, right? Now again we will reduce the in degree, that is from 1 to 0, from 2 to 1. Now we need to push the element with the in degree of 0, right? So we will push 0, right? So add 4 here. After that, we will pop this 2. What are the neighbors? 3 only. We will reduce the in degree of 3, that is 0. Okay, and we will push in the result. What we need to push? 2, and here 3, right? Again we will check the next element, that is 0. Okay, neighbors are not there, so we will push in the result, right? After that, 3, we will pop this out. What are the neighbors? 1. We will reduce the in degree, 0. Now we will add this 1 in the queue and 3 in the result. We will remove this 1, in degree is 0. We will add in the result. Got it? In this graph, what is the total degree? 1, 2, 3, 4, 5. 5 is the edges. What is the degree? For 2 it's 1, for 0 it's 2, for 3 it's 1, for 1 it's 2, it's 6. Okay, 1, 2, 3, 4, 5 and 6. So total degree is the total edges. If it's clear, let me tell you one more concept here. Now we can also find the cycle. Let's say if there is some cycle in this graph, we can find this. How? Let's say at the end, if the number of elements in this node is not equal to the total number of nodes, we can say there is a cycle. Okay, let's create this. Let's say 0 and let's say 1. This is the graph, right? So okay, and let's say this is the graph. Clear? Now this topological sort using BFS, we can also find if there is a cycle or not. Okay, let's say this is the graph. Okay, what is the in degree initially? It's 0 for this. What is the in degree for this? It's 2, right? It's 2. For this it's 1, correct? For this it's 1. Now we will start from this node 0, correct? In the BFS in the queue we will add this 4, right? Nothing is 0. Okay, we will proceed with these nodes in the queue. We will remove this 4. Now children, 5 is there. We will reduce the in degree to 1, right? Now is there any other node with in degree of 0? No, it's not there. So we can say at the end we will check the size of array, that is currently 1, with what? With the total number of nodes. If they are not equal, we can say there is a cycle in between. Okay, if result dot size is not equal to total nodes, we can say cycle is there. So this is the concept of cycle. Or we can also say we can't arrange the nodes in order, right? We can also say this, right? Okay, this is important. This concept you will be using in the next question. Okay, so let's write the code for this. So we will be using this function only. Okay, and okay, so we are already having this adjacency list. Remove this DFS. Let's say Kahn. Okay, so in this what we will have? We need to calculate the in degree, right? In degree equal to new int of size what? V, right? After that, what is the step 1? Step 1 is count the in degree for all the nodes. So step 1, count in degrees. Okay, how we can do? We can do using the adjacency list. Let me tell you how. I less than v and I plus plus, right? After that we will get the adjacency list, the neighbors, int neighbor adjacency dot get I, and we will increase the in degree of the neighbor. In degree of neighbor plus plus. Okay, what I'm saying here, let's say we are having the adjacency list. Let's say from this example, for 5 we are having what? 0 and 2, right? For 2 we are having 3, for 3 we are having 1, for 0 we are having nothing, for 4 we are having 0 and 1, 0 nothing. Okay, so this is the adjacency list. Now what is the in degree of 0? It's 2, right? Because it's coming for 5 also as a neighbor, for 4 also as a neighbor. So when we are traversing the neighbors of this 5, we will do in degree of this 0 plus plus, it will be 1 now, correct. After that, when we are traversing 0 here, we will do in degree of this plus plus, so it will be 2. Okay, so using the neighbors, we are increasing the in degrees, right? So got it, these all are the neighbors. This 2 is the neighbor, this 0 is the neighbor. So if it is the neighbor, we need to increase the in degree. Neighbor, let's write it here. Neighbor means in degree. Okay, means there is a incoming edge. Okay, right. So this is how we will get the in degree. Now what is the second step? Second step was push all the nodes with in degree equal to 0 in the queue. Okay, so step 2, push all in degree 0 in queue. Okay, we need to have a queue of type integer, queue equal to new linked list, correct. So we are having the queue. Now we will traverse the nodes, that is 0 to v, int I equal to 0 till v I plus plus, and we will push the nodes with in degree equal to 0. So if in degree of I equal to 0, q dot add, right, add what? I. Okay, so we will add the all the nodes with in degree equal to 0, right. After that, what was the third? Process the queue, right, process the queue. How we can process the queue? Using that while loop. Process the queue while queue is not empty, we will start it, right. Now in the queue we need to remove the element, right. Int current node, we can say queue dot pop, correct, it's Paul, right. We will remove the node. After that, we will add in the result. Now for the result, we need to make a int array or list of integer arr topo equal to new array list. Topo dot add, we need to add this node, right, the result. So add it. Now we will traverse its neighbors, its child. For loop int neighbor on what we need to apply? We need to apply the for loop on this neighbors dot get what node, right. After that, we will reduce the in degree of the neighbor minus minus. Then what we need to do? We will check if in degree of this neighbor is equal to 0, push it in the queue dot add what we need to add, neighbor. Okay, if it's equal to 0, then we will add it, right. And that's it. At the end, we will be returning this array, this chopo, right. So let's return this here, list of integer arr equal to this chopo. Okay, and then we will simply print it, int I equal to 0, I less than arr dot size I plus plus. System dot out dot println arr dot get I plus. Okay, right, let's run this. We need to return it also. Return topo. Okay, so we got the answer. This is the valid output, right? Let's send the order. Got it, guys? So now one more thing is there. We can also check cycle is there or not, right? For that, what we need to do? We need to check if topo check for cycle or the valid order is possible or not, right? If topo dot size is not equal to what? V was the count, right? Yes. Then we can say system dot out dot println cycle is there. Cycle is there. Understood? This is the simple logic for checking for the cycle. Now what is the time complexity for this? It will be same. We are traversing each and every node, and we are traversing its neighbors, every edge, right? So this will be for the edge and this will be for the nodes. So the time will be of v plus e space. Now space again, it will be, if we are including adjacency list, it will be o v plus e, okay, and otherwise it will be of v. Got it? Okay, so this is the question. So we will, these both are same, we will check this one first because this is the similar. Okay, so what is the question? There are total of num courses you have to take label from 0 to num courses minus 1. Okay, 0 indexed nodes are there. You are given an array prerequisites where prerequisite I is equal to a of I, b of I, indicates that you must take course b1 first if you want to take course b1. Okay, and we need to return the ordering of the courses you should take to finish all the courses. So let's copy this. Okay, so this is the question given. You are given two basically edges are given. Let's copy the example also. Let's copy this example. Okay, so basically you are given the total number of courses, that is 4 in this case, and you are given the prerequisites array where prerequisite I is equal to a of I and b of I. That means you can take b1 course first if you want to take a1. Okay, so we can say we need to take b1 first before a1, right? This is what they are saying. You must take course b1 first if you want to take a1, correct? b1 should be before a1, right? We can write it like this, correct? Now is it same? We can take this b1 as one node, a1 as one node, and we can say what is the property of this topological sort? It is like this: u should come before v, right? Is it same, right? That's what they are saying. b1 should come before a1. We can apply topological sort here, right? So this is one edge. We can say this is edge, one edge, right? So in the question, in the example, total 4 nodes are there. What are the edges? 1 and 0, 2 and 0, 3 and 1, 3 and 2. Okay, let's write it. So we can write it like this: 0 should come before 1, right? And 0 should come before 2, 1 should come before 3, and 2 should come before 3. These are the edges, right? These are the edges. Now, how can we do this? Anyone? We are given the edges. We need to find the topological sort. We need to return this output, right? The sort, the output of the topological sort. Okay, so can we find the adjacency list using these edges? Yes, we can. So what should be the adjacency list? It will be like for 0, what are the elements? It's 1 and 2, right? For 1 it's 3, for 2 it's 1 and 3, correct? This is the adjacency list. Now we have the adjacency list. Can we apply this topological sort, topo sort, using BFS? Because can we apply this? First tell me this part. Can we apply topological sort using BFS? Understood till this point how we are getting the edges from this prerequisite and how we are converting this into the adjacency list? So this is clear how we are getting the adjacency list. Now afterwards it's clear, right? It's easy. We can simply apply the topological sort on this array list. We can find the in degree. What was the steps? Where is the steps? These are the steps, right? Let's copy this. Okay, we will apply these steps. First we are having the adjacency list. List is given. List we have to find, right? So we found the adjacency list using the edges. After that we need to count the in degrees for the hull. These are the steps. We will found the in degrees from this adjacency list. Push all the nodes with in degree equal to 0 in the queue, right? Start traversing the queue. We will pop the element, push in the result, check for the neighbors, reduce the in degree. Basically what we are doing, we are telling the sequence that which node should come first, right? That's what we need to find. If it's 0 and 1, this 0 should come before this 1, right? That's what we are doing in the topological sort. We are having the output in the topological sort order. Topological sort is doing what? We are getting the order of what? If there is a edge u and v, it makes sure that u should come before v, right? This is the definition of the topological sort, and that's what we are doing here. We are given the edges and we need to make sure this, after combining them, this definition should be maintained. This 0 should come before 1, this 0 should come before 2, this 1 should come before 3, right? We are having this adjacency list. We can also make the graph like from 0 it's going to 1, and from 0 it's going to 2, right? And from 1 it's going to 3, then from 2 it's going to 3, right? First we need to make sure it's a DAG, directed acyclic graph. Its cycle is not there, right? And directions are there, so we can apply the topological sort. Also if cycle is there, we can still apply the BFS topological sort using BFS. In that we can find if cycle is there or not. Remember last thing, we are comparing size of the array, the resultant array, with the total number of elements, right, for cycle. So this is the graph. Now we need to find the order. Simple, right, as we did earlier. Basically the initial part is important. If you get this, like we are given this prerequisites and we can convert this into the edges of the nodes, then we can simply apply the topological sort. Shall we code it? So this was the question, right? What we need to do? Okay, first we are given this prerequisite, that is the edges, right? 0 1 2 0, these are the edges in the reverse order, right? So first we need to create the adjacency list. So list of integer adj equal to new array list. Correct. We initialized this array list. After that, one we need to maintain as in degrees. In degree new int of size num courses, that is equal to the number of nodes, right? After that, let's write it here. Consider courses as nodes. Okay. Now we need to create a adjacency list using this prerequisite array. Okay. So basically, if we are given 1 and 0, it should be what? It should be like this. First 0 will come, then 1. Okay. So we need to increase the in degree of 1 and add this one as the neighbor of 0. Got it? So for loop int I equal to 0, I less than what? The num courses. Okay. Currently I am initializing this list, basically adj dot add new array list for every list, basically till this length. Okay. Now we will start traversing the elements and this prerequisite, right? So let's say pre on this prerequisites, we will get the array, right? Now from the array, this is the thing. So it will be like what? adj dot get. In what we need to add the neighbor? We need to add the neighbor of 0 and we need to add 1, right? So what is 0? 0 is pre of 1, right? It's pre of 1. And after that, dot add pre of 0. Got it? In this way we will add like this, 0 to 1, right? From this we will get this. Understood? And in the same step we can also increase the in degree, right? No need to have a different for loop. In degree of what? In degree of pre of 0 plus plus. Got it? From this step, get adjacency list and in degree array. Okay, so this part is done. We got the in degree. Now what else? What we are doing here, after creating the in degree, second step is push all the nodes. Let's copy this only. Push all the nodes with in degree of 0 in the queue. Okay, we pushed all of the nodes with in degree of 0 in the queue. After that, process the node, add the result in the queue. We will what? We will create one topological array, basically the order, right? And then we will start with the processing of the queue. We will get the element, the node from the queue. Okay, we will add it in the topological array, the sorting array, right? Then we will check its neighbor from the adjacency list, and we will reduce its in degree. If it's equal to 0, we will add in the queue. Okay, that's it. After that what we need to return? We need to return it as a int array. So convert it. Let's make it first int final, let's say result equal to new int of size what? Num courses, right? Num courses. And before that we can also check if there is a cycle or not, Hana? So check for cycle or order, or if order is not possible. Both are same thing. If num, basically topo dot size is not equal to num courses, then return empty array, return new int of size 0. Okay, otherwise we will create the final result of size num and we will push I less than num courses I plus plus. So final res of what? I is equal to topo dot get I, return final res. Let's run this. Compilation error, adj expected. Okay, instead of v we need to use this. We copied the same code here also, I guess. Something is there or not? Okay, it's accepted now. Let's submit. So it's accepted. Okay, so basically we are using the simple algorithm, right? The same code from this BFS topological BFS one. Understood, guys? So this is the first question and let's check this question. So it's same basically. Here what we need to do, we need to check if these pairs are correct or not. Okay, so you are given the array prerequisite and this thing must take the course, everything is fine. Return true if you can finish all the courses, otherwise return 0. That means we need to check if our order is correct or not, if we can finish all the nodes, right? Got it? Here just we need to check the cycle is there or not, right? Understood what we need to do here? Everything will be same, just we need to check if we can finish all the courses or not. If dependency is not there, let's say if cycle will not be there, then we can finish every node, right? We can go to every node, we can finish and we can say it follows the dependency and we got the output. But if cycle is there, that means we can't complete all the nodes, right? Let's say here this is the code, right? Let's say instead of this we are having this, right? Now what? For 1 we need to complete 2. It's not cycle yet, convert it like this. Okay, now for 0 we need to complete 2 first, right? And for 1, for 2 we need to complete 3, for 3 we need to complete 1, for 1 again we need to complete 0. So we can't complete all of the courses, right? So it's not possible. So here in this question we just need to check if cycle is there or not. So we can copy the same code from here. Okay, and if cycle is there, that means here, right? This is where we are checking the cycle. If cycle is there, return false, otherwise return true. If cycle is there, that means we can't complete all of the courses, right? Because for each and every course dependency will be there. So it's accepted, right? So just we need to check the cycle. Okay, and here one more thing, we can optimize it. Instead of using this array, instead of storing the result, we can simply count processed courses. Initially it will be 0, and instead of adding in the queue we can say processed. That means the number of courses are done till now we are increasing, right? And at the end we can simply check this number with the total number of counts. That means what we are doing here, we are increasing the number of processed courses. That means this number of courses we have completed. At the end we will check the same. If it's not equal to the total number of courses, that means something is pending. There is the cycle, right? This is basically same thing, the size of this, right? Just we are saving our space. Let's run this. It's accepted.